One.
Hello, class. This is Mr. Filsick. Today we're going to learn about the history of the atom. Our LEQ for today is how can we model the structure of an atom? First off, what is a model? Um, is a model what you see on the screen right now? Is it people who dress up in fancy clothes and walk down runways? Well, in the fashion world, that's a model, right? But in science, a model is something a little bit different. Let me show you something to help you out. So right here you see a model of the solar system. Um, Obviously, this model of the solar system is much smaller than the actual solar system. If you look in here, in case you didn't know, the sun is a lot bigger than it looks like the size of a soccer ball, right? So why do we use a model like this to describe the solar system? And obviously, it's because the solar system is huge. Imagine how big the solar system is. If you were to hop in a car right now and travel at 1,000 miles per hour toward the planet of Neptune, which is obviously a crazy idea, it would take you 342 years for you to get there. So in other words, you wouldn't get there because you'd probably be dead. Um, the solar system is huge. That's if you're going 1,000 miles per hour, right? And that's why we use a model. So what does this model help us do? A model is a representation of an object or system that cannot be experienced directly, right? We can't experience the solar system, so we need to use a model to help us represent it. Models help us understand things that are difficult to imagine otherwise, like things that are too big or too small to see. The reason I underlined or too small, guys, is because that's what we're going to look at today. Also, it's important to know, guys, models can be changed over time. So you might come up with a model for the solar system, or back in the day, scientists or philosophers thought the Earth was the center of the solar system, right? But as discoveries were made, we realized the sun was the center of the solar system. So that model completely changed, right? Models can be changed over time as new discoveries are made, and we're going to see that in action today on this video, okay? In case you didn't know, guys, atoms are tiny. Atoms, we've talked about them a lot in class so far, right? We've talked about the periodic table of elements. Each of the elements is a different type of atom. Atoms are tiny. There is no way you can see an atom with your eye, even under a microscope. They're so small. So scientists have to use methods other than sight, like different experiments, in order to determine what an atom looks like. Today we're going to look at a timeline of discovery. These five dudes, Democritus, John Dalton, Joseph Thomson, Ernest Rutherford, and Niels Bohr, throughout the last 2,500 years have helped us figure out what an atom looks like, and we're going to learn about it right now. So buckle up because we're going to do it real quick, okay? First off, we have this guy named Democritus. He lived in 400 BC. That means he lived 400 years before Jesus. This guy's old, right? This guy was walking on the beach one day, looking at the sand on the beach, and he started thinking about the smallest things on the planet. He said, if you keep cutting something in half over and over and over, he said that you'll finally reach a particle that is so small that it can't be cut any smaller. And he called that particle atomos, meaning not to be cut. So literally when you say the word atom, it's coming off the word not to be cut. It's so small it can't be cut. Or at least that's what Democritus thought. Democritus thought atoms looked like this. In this case, little circles, right? They were small, hard particles that were all made of the same material, but were different shapes and sizes. So very simple model Democritus came up with of what an atom looked like. So you can draw that on your sheet. This theory, though, was ignored and forgotten for more than 2,000 years. So this guy had this idea in 400 BC. 2,000 years of history went by, no one paid attention to it until this guy named John Dalton. So John Dalton was around in 1803. He conducted a lot of experiments that eventually led to basically proving that atoms did exist. And he came up with the following three ideas. All matter is made of atoms. We've kind of already talked about that. Atoms cannot be created nor destroyed in a chemical reaction. You guys already know that. And atoms of one element are exactly alike, but they're different from atoms of other elements. In other words, every atom of hydrogen is like every other atom of hydrogen. Every atom of helium is like every other atom of helium. However, hydrogen and helium atoms are different. And that's what he came up with. But he still thought the atom looked like this, right? Basically just a circle, a very simple circle. Then we had this guy in 1897 named Joseph Thomson. He did an experiment by passing by passing electric current through a gas, and he discovered negatively charged particles. Basically what that means is that this is the first time we saw that atoms are actually made of even smaller particles. So they're actually not, quote unquote, uncuttable. They're made of even smaller particles. And he developed what we call the plum pudding model, or what I call the chocolate chip cookie model. Looks like this, right? It looks like a chocolate chip cookie. It's still a circle, a sphere with little what are called electrons sprinkled about like a chocolate chip cookie. So you can draw that in for Thomson's model. Then we had a guy in 1911s. This is about 15 years later, a guy named Ernest Rutherford. He did an experiment which involved firing a stream of tiny, what are called alpha particle radiation at gold, a sheet of gold, a very thin sheet of gold. What he noticed is that, as you can see here, most of the particles came through and literally just went right through the sheet. But every once in a while, a particle would bounce back for some reason. And what he theorized based on that is that atoms do have electrons. So he's building off the previous model, but they're actually mostly open space. Atoms aren't like chocolate chip cookies that are all filled in, right? Most of an atom is made up of empty space with a very dense part in the center that he called the nucleus. The nucleus is tiny compared to the rest of the atom. In his model, he had the nucleus in red right here and everything else in the green around here that was mostly empty space. We know now, though, this red part is actually way smaller than that even. Lastly, we have a guy named Niels Bohr, and this is the most important model we're going to look at today because you're going to be looking at this model a lot in this unit. Niels Bohr conducted experiments to show, this is in 1913, so a little over 100 years ago, to show that electrons, these negatively charged particles, orbited the nucleus like planets orbiting the sun. It became known as a planetary model. So it looks, as you can tell, you can see why it would be called a planetary model. It looks like there's a sun in the middle with a bunch of planets around it. This is the model that you'll be learning about in this unit, and this is the model you'll be learning about today. Niels Bohr model, as seen right there. Obviously, more models followed, guys, including one called the wave model that we'll learn about later. And just like any science, as science works, as more discoveries are made, atomic models will continue to change as more information comes around, right? But next, what you're going to do, you're going to open the simulation on Schoology, and you're going to explore the Bohr model of an atom. While you explore, remember what you just learned. Remember how many scientists have contributed to the creation of the model that you're going to be using, right? Over the past 2,000 years, from way back here in Greece with Democritus to in 1913 with Niels Bohr, they finally came up with this model that we're going to be using today. So go to the simulation on Schoology, start exploring it, and learn about the different parts of the subatomic particles inside of an atom.